Hello, and welcome to Galactics. Tonight, we're spending some time with one of the most recognizable sights in the entire solar system, a planet so visually striking that the first astronomers to see it through a telescope genuinely didn't know what they were looking at. Saturn has been watched by human eyes for thousands of years. Ancient civilizations tracked its slow movement across the sky, named it after gods, and built entire systems of meaning around it, long before anyone understood what it actually was. Tonight, we'll move through Saturn's turbulent atmosphere and its impossible storms, explore the rings in more detail than most people ever get to, and sit with the questions that even our best spacecraft haven't been able to answer. Without further ado, let's get into it. Saturn has been in the human sky for as long as there have been humans to look up. It doesn't announce itself the way a comet does or flare like a meteor. It simply moves, slowly, steadily, tracing its way through the constellations over the course of decades. Bright enough to notice, slow enough to feel significant. To the ancient world, that mattered. The Babylonians were among the first to track it with any precision. Their astronomical records, some dating back nearly 3,000 years, show careful observations of Saturn's position across the sky, logged on clay tablets, cross-referenced with other celestial events, used to predict what might come next. They called it Kayamanu, a wanderer, something that moved when everything else seemed fixed. The Greeks inherited much of that tradition and handed it to Rome, where the planet was named for Saturn, god of time, of harvest, of things that end and begin again. That name carried weight. There was something about this slow, distant light that felt ancient even to people who had no idea how far away it was. For most of human history, that's all Saturn was. A point of light with a name and a story attached to it. Then came the telescope. In 1610, Galileo Galilei turned one of the earliest telescopes towards Saturn and saw something that made no sense. The planet appeared to have companions. Two round shapes flanking it on either side, close enough to almost touch. He sketched what he saw and described it as a triple planet. Three bodies traveling together through the sky. He had no framework for what he was actually looking at. When he checked again 2 years later, the companions had disappeared. Saturn looked perfectly round, ordinary, alone. Galileo was baffled. He wrote about it with something close to frustration. A planet that seemed to devour its own children, then deny it had ever happened. What he was seeing, without knowing it, was the ring system changing its angle relative to Earth. When the rings are edge-on, they nearly vanish. When they're tilted, they look like bulging shapes on either side of the planet. His telescope wasn't sharp enough to resolve what they actually were. He died in 1642 without ever understanding what he'd seen. It took another generation to get there. In 1655, the Dutch astronomer Christian Huygens pointed a significantly better telescope at Saturn and saw the truth, or at least the beginning of it. The companions weren't companions at all. Saturn was surrounded by a thin, flat ring, tilted at an angle, not touching the planet on either side. He also, in the same period of observation, discovered Titan, Saturn's largest moon, a point of light orbiting steadily nearby. In the space of a few years, Saturn went from a confusing blur to something genuinely complex. A few decades later, Giovanni Cassini pushed the understanding further. In 1675, he noticed that the ring wasn't a single solid structure. There was a gap running through it, a dark band dividing the ring into two distinct regions. That gap now bears his name. Cassini also discovered 4 more moons, steadily building the picture of a system far more layered than anyone had imagined. And still, all of this was happening from Earth, through glass lenses in candle-lit observatories by people with no way of knowing that the ring system they were squinting at stretched nearly 300,000 kilometers from edge to edge. Saturn is the 6th world from the Sun, sitting at an average distance of about 1.4 billion kilometers. Light from the Sun takes more than an hour to reach it. At that distance, the Sun would look noticeably smaller in Saturn's sky. Still bright, still the dominant light source, but reduced. Distant. A reminder of just how far out we're talking. In terms of size, Saturn is the 2nd largest planet in the solar system, behind only Jupiter. Its diameter is nearly 10 times that of Earth. You could fit over 700 Earths inside its volume. Those numbers are familiar territory for anyone who spends time thinking about space, but they still don't fully land until you try to hold them against something real. What does land and tends to stay with people is the density. Saturn is the least dense planet in the solar system. Its average density is about 0.69 grams per cubic centimeter. Water is 1.0. That means if you could find a body of water large enough, Saturn would float. That fact gets repeated a lot, and it's easy to let it slide past, but it's genuinely worth pausing on. A planet, floating, a world nearly 10 times the diameter of Earth, with 95 times its mass. And it is less dense than the liquid that fills our oceans. The reason is composition. Saturn is made almost entirely of hydrogen and helium, the 2 lightest elements in the universe. There's no solid surface to speak of. If you descended into Saturn, you wouldn't hit ground. You would move through layers of increasingly dense, increasingly pressurized gas. The atmosphere gradually thickening around you, the pressure building, until the gas itself began to behave less like a gas and more like a liquid. Deeper still, under pressures difficult to fully imagine, hydrogen enters a state that doesn't exist naturally anywhere on Earth. Metallic hydrogen, a phase where the electrons are stripped free, and the hydrogen conducts electricity like a metal. It's not solid, not gas, not liquid in any conventional sense. It's something else. And it's thought to make up a significant portion of Saturn's interior. At the very center, there may be a dense rocky core, though even that is uncertain. The pressures at Saturn's heart are so extreme that the materials there behave in ways our physics can describe mathematically, but has never been able to observe directly. Saturn also spins extraordinarily fast for something its size. Its day is just over 10.5 hours long. That rapid rotation has a visible effect on the planet's shape. Saturn is noticeably flattened at the poles and bulging at the equator, an oblate spheroid stretched outward by its own spin. The difference between its polar and equatorial diameter is significant enough to measure easily, nearly 12,000 kilometers of difference. It's one of those details that makes Saturn look slightly wrong when you first notice it, like a planet that's been gently pressed from both ends. There's one more thing about Saturn's interior worth mentioning. Saturn radiates more energy than it receives from the Sun, not by a dramatic amount, but measurably more. Jupiter does the same thing, likely from residual heat left over from its formation. But Saturn's case is slightly different. It's thought that helium, which is denser than hydrogen, is slowly sinking toward Saturn's core over billions of years, and as it falls, it releases heat. A planet generating warmth from within through the slow gravitational settling of its own interior. It's been doing this for a very long time. The image that comes from all of this isn't the solid, rocky world we're used to picturing when we think of a planet. Saturn is more like a vast, layered sphere of compressed gas and exotic matter, with no shore to stand on, no ground beneath your feet, just depth upon depth of pressure and heat and chemistry that we've only begun to understand. And all of that is before you even get to the rings. From a distance, Saturn has a softer appearance than Jupiter. Where Jupiter is streaked with vivid bands of orange and brown and cream, Saturn tends toward pale gold and muted amber, its bands visible but gentler, like a watercolor version of its larger neighbor. For a long time, astronomers assumed this meant Saturn's atmosphere was simply less active. That assumption was wrong. The banding comes from the same basic mechanism as Jupiter's. Alternating jet streams moving in opposite directions, east and west, carving the atmosphere into distinct latitudinal zones. But Saturn's upper atmosphere is colder than Jupiter's, and a thick haze of ammonia ice sits high up in the cloud layers, muting the colors underneath. The drama is there, it's just partially hidden. The wind speeds are not hidden at all. Near Saturn's equator, winds have been measured at close to 1,800 kilometers per hour. That's roughly 5 times the speed of the most powerful hurricanes ever recorded on Earth. These aren't storm winds, they're the baseline. The ordinary state of Saturn's upper atmosphere is moving at a speed that would be catastrophic by any earthly measure. Storms, when they come, are something else entirely. Saturn experiences what are called great white spots, periodic eruptions of bright storm activity that appear roughly every 30 years or so, tied loosely to Saturn seasons. They tend to begin as a single bright point and expand outward, sometimes growing until they wrap entirely around the planet. The leading theory is that heat building up in the lower atmosphere eventually becomes unstable and punches upward, breaking through the haze layer in a massive convective eruption. The most recent one occurred in 2010 and 2011, and it was exceptional even by Saturn's standards. What began as a small bright spot in the northern hemisphere grew into a storm system that eventually encircled the entire planet. It stretched for hundreds of thousands of kilometers. The Cassini spacecraft, which was in orbit around Saturn at the time, had a front row view, and the data it sent back showed thunderstorm activity more powerful than anything previously observed on Saturn. Lightning strikes releasing energies that dwarfed anything in Earth's atmosphere. By the time it faded, it had been visible for months. But the storm that tends to stop people isn't the great white spot. It's something quieter looking, and in some ways far stranger. At Saturn's North Pole sits a persistent hexagonal cloud pattern, a 6-sided geometric structure that has been there, as far as we can tell, for decades. Each side of the hexagon is roughly the width of Earth. The entire structure rotates, maintaining its shape, its edges surprisingly sharp and defined against the surrounding clouds. When Voyager first photographed it in the early 1980s, scientists assumed it might be a temporary feature, something that would shift and dissolve over time. It was still there when Cassini arrived more than 2 decades later. The hexagon is a standing wave, a pattern locked into Saturn's atmosphere by the interaction of jet streams at that latitude. On Earth, polar jet streams meander and shift, producing the wavy, irregular patterns that drive so much of our weather. On Saturn, something about the conditions at the North Pole has locked that wave into a stable, 6-sided shape that has persisted for as long as we've been able to observe it. The mathematics of fluid dynamics can produce hexagonal patterns under the right conditions. laboratory experiments have recreated similar shapes in rotating tanks of liquid, so in one sense, we understand why it exists. In another sense, seeing a hexagon the size of multiple Earths sitting calmly at the top of a gas giant still doesn't feel like something that should be real. At the South Pole, the situation is different. Instead of a geometric standing wave, Cassini found a massive hurricane-like vortex, a tightly wound spiral storm system locked to the pole, with an eye clearly visible at the center. On Earth, hurricanes drift and weaken as they move over land or shift in latitude. Saturn's south polar vortex has nowhere to drift. It sits there, spinning, sustained by Saturn's own internal heat rising upward. Two poles, two completely different structures, both persistent, both enormous. Saturn's atmosphere, it turns out, is not soft at all. It just takes time to reveal what it's doing. There is no other site in the solar system quite like Saturn's rings. Even after everything we've learned about them, the chemistry, the physics, the orbital mechanics, they still manage to look like something that shouldn't be there. A flat, luminous disk wrapped around a planet, casting shadows, catching sunlight, stretching outward in near-perfect symmetry. They are almost entirely made of water ice. Not rock, not dust primarily, not the kinds of debris you might imagine when you think of a ring system. The vast majority of Saturn's rings are composed of water ice particles, ranging in size from tiny grains to chunks as large as a house. Some larger, boulder-sized objects exist within the rings as well, but the overwhelming character of the system is bright, reflective ice, which is why the rings are so visible. They catch sunlight and throw it back with remarkable efficiency. What makes the rings even more striking is their dimensions. The main ring system stretches roughly 280,000 kilometers from its inner edge to its outer edge. To put that in context, the distance from Earth to the Moon is about 384,000 kilometers. Saturn's rings span most of that distance, and yet, for all that width, they are extraordinarily thin. In most places, the rings are only about 10 to 30 meters thick, some regions possibly thinner. The ratio of width to thickness in Saturn's rings is comparable to a sheet of paper scaled up to the size of a city block. Something that vast, that thin, held in place by gravity and orbital mechanics alone. The rings are divided into distinct regions, each with their own character. The innermost rings, the D and C rings, are faint and relatively sparse. The B ring is the brightest and densest, the most visually dominant part of the system. Then comes the Cassini division, a gap that appears dark from Earth and was long thought to be mostly empty. Cassini the spacecraft revealed it isn't truly empty. It contains faint ringlets and dust, but it is significantly less dense than the rings on either side of it. Beyond that sits the A ring, broad and bright, containing its own internal structures. Then the narrower F ring, kept surprisingly sharp-edged by the gravitational influence of two small moons orbiting just inside and outside it. Further out, the G and E rings are faint and diffuse, more like halos than the crisp structure of the inner system. The Cassini division itself exists because of orbital resonance. The moon Mimas orbits Saturn at a distance that puts it in a 2-to-1 resonance with particles in that region, meaning a particle at that location completes exactly 2 orbits for every 1 orbit Mimas completes. Over time, the repeated gravitational nudges from Mimas pull those particles out of that zone, clearing the gap. It's a slow process, operating over millions of years, but the result is visible from Earth with a modest telescope. Shepherd moons perform a similar function at ring edges throughout the system. Small moons orbiting just inside or outside a ring exert gravitational pressure that keeps the ring material corralled, preventing it from spreading outward or drifting inward. The F-ring's unusually sharp edges are a direct result of this shepherding effect, maintained by two small moons named Prometheus and Pandora. There are also features within the rings called spokes. Voyager first spotted them in the 1980s. Dark radial streaks appearing across the B-ring, extending outward from the planet like the spokes of a wheel. They appeared and disappeared on timescales of hours, which made no sense under purely gravitational models. Gravity should smear any radial feature into a curved shape almost immediately at orbital speeds. The leading explanation involves electrically charged dust particles being lifted above the ring plane by Saturn's magnetic field, essentially hovering briefly before settling back down. Cassini confirmed their existence and observed them changing with Saturn's seasons, more prominent at certain times than others. And then there is ring rain. Material from the rings is constantly being lost. Charged particles get drawn along Saturn's magnetic field lines and fall into the upper atmosphere. A slow but measurable drain on the ring system. Estimates vary, but somewhere between 1 and several tons of ring material may be falling into Saturn every second. Over geological time, that adds up, which raises a question that the rings themselves can't answer on their own. How long have they been there, and how much longer will they last? The rings look permanent. They look like they've always been there and always will be. Neither of those things is likely true. The question of where Saturn's rings came from has been debated seriously since we had enough information to form a real opinion about it. And, even now, with decades of spacecraft data to draw from, the answer isn't settled. There are leading theories. There are strong arguments. But the origin of Saturn's rings remains genuinely open. The oldest idea, and in some ways still the most intuitive, is that the rings are primordial, left over from the same cloud of gas and dust that formed Saturn itself roughly 4.5 billion years ago. Under this model, the rings are as old as the planet. Material that never coalesced into a moon, held in place by tidal forces, slowly spreading into the flat disk we see today. The problem with this idea is the ice. If the rings were 4.5 billion years old, they should be dirty. The solar system is not a clean place. Micrometeorite impacts, interplanetary dust, cosmic debris, all of it would have darkened and contaminated the ring material over billions of years. But Saturn's rings are bright. Remarkably, almost suspiciously bright. The B ring in particular reflects light with an efficiency that suggests relatively uncontaminated ice. Ice that hasn't been sitting in space for 4.5 billion years, accumulating grime. This pushed scientists toward a different conclusion. The rings might be young, not young in human terms, but young in geological and cosmic terms. Estimates from Cassini's data suggest the rings may have formed somewhere between 100 million and 400 million years ago, which means they didn't exist when dinosaurs walked the Earth. Which means, on the timescale of the solar system, we are watching something relatively recent. If that's true, something had to create them. The leading candidate is a destroyed moon. Under this model, a medium-sized icy moon once orbited Saturn at a distance closer than where the rings now sit. Something disrupted it, possibly a gravitational interaction with another large body, possibly a massive collision, and the moon came apart. Tidal forces prevented the debris from reaccumulating into a new moon, and over time it spread into the ring system we see today. There's a variant of this theory that's particularly interesting. Some researchers have proposed that a large moon, one with a rocky core and an icy outer layer, was pulled close enough to Saturn that tidal forces stripped away the ice while the denser rocky core survived and was eventually ejected from the system. The stripped ice became the rings. The rocky remnant left the solar system entirely or was absorbed into Saturn. It's a dramatic origin story for something that now looks so serene. The Roche limit plays a central role in all of this. Every large body has a Roche limit, a distance within which tidal forces overcome the gravitational cohesion holding a smaller object together. Inside that limit, moons can't form. Material that gets too close gets pulled apart. Saturn's rings sit almost entirely within Saturn's Roche limit, which is why they exist as rings rather than coalescing into a new moon. The same physics that may have destroyed the moon that created the rings is the physics that prevents those rings from reassembling. Outside the Roche limit, things behave differently. Small moons can form and survive. And there's evidence, within the rings themselves, of clumping. Regions where material is slowly trying to accumulate into something larger, only to be pulled apart again by tidal forces before it gets very far. The rings are dynamic in ways that aren't obvious from a distance, and they are temporary. The ring rain mentioned earlier, the slow drain of material into Saturn's atmosphere, combined with other loss mechanisms means the rings are being depleted. They won't last forever. Current estimates suggest they may be largely gone within 100 million years, perhaps less. In the context of a 4.5 billion-year-old solar system, that's not very long. There's something quietly striking about that. Every other planet in the solar system has been observed and catalogued and studied. But Saturn, right now, in this particular window of cosmic time, looks like this. Ringed, luminous. The version of Saturn that exists in every astronomy textbook, every telescope image, every child's drawing of the solar system. That version of Saturn is not the default, it may be the exception. We happen to be here while the rings are still there, and given the timescales involved, that might be worth noticing. Saturn does not travel alone. As of the most recent counts, Saturn has 146 confirmed moons, the most of any planet in the solar system. They range from tiny captured rocks barely a kilometre across to worlds large enough to have their own atmospheres, their own weather, their own chemistry. Some orbit in tight, orderly paths close to the planet. Others loop out in wide, irregular trajectories that suggest they were captured long after Saturn formed. It is, by any measure, a crowded system. Titan is the largest of Saturn's moons, and one of the most extraordinary objects in the solar system. It's larger than the planet Mercury. It has a thick nitrogen atmosphere, denser than Earth's at the surface, dense enough to hide its surface entirely from visible light. Beneath that orange haze sits a landscape that is, in some ways, eerily familiar. Rivers, lakes, seas, rain, erosion, all operating through a hydrological cycle not unlike Earth's, except the liquid isn't water. It's methane. Liquid methane filling lakes near the poles, evaporating, forming clouds, falling as rain onto a surface where the temperature sits around -179 degrees Celsius. It is the only world beyond Earth known to have stable liquid on its surface. Titan deserves far more time than this section can give it, and it will get that time. For now, just hold the image. A moon with weather, with seasons, with shorelines, in orbit around Saturn. Enceladus is smaller, much smaller, but in some ways even more immediately compelling. It's an ice-covered moon, roughly 500 kilometers across, and it is geologically active in a way that shocked planetary scientists when Cassini flew close enough to see it clearly. Near the South Pole, a series of long fractures, nicknamed the tiger stripes, are venting material into space. Jets of water vapor and ice particles erupting continuously from beneath the surface, reaching hundreds of kilometers into space. That material feeds Saturn's E-ring. But more significantly, it tells us what's underneath. Beneath Enceladus's ice shell sits a global subsurface ocean of liquid water. A salty ocean with hydrothermal activity on the seafloor, meaning warm water interacting with rock. The same basic conditions found at deep ocean vents on Earth where life thrives in complete darkness. Enceladus is actively venting the contents of that ocean into space, which means any spacecraft passing nearby is essentially sampling it directly. It is one of the most compelling places in the solar system to look for signs of life beyond Earth. And that conversation, too, deserves its own time. Mimas is a different kind of remarkable. It's a small, heavily cratered moon dominated by a single enormous impact crater, Herschel, which spans nearly a third of Mimas's diameter. The resemblance to a certain fictional space station has been noted by essentially everyone who's ever seen an image of it, and the comparison is hard to avoid. What's interesting is that Mimas, despite its dramatic appearance, is thought to be one of the less geologically interesting moons in the system, so largely inert, mostly ice, shaped more by ancient collisions than by any internal activity. Though recent data has raised questions about whether there might be something going on beneath the surface after all. Mimas has a way of resisting easy conclusions. Iapetus presents a different kind of strangeness. One hemisphere is almost perfectly white, the other is almost perfectly black. The contrast is so extreme, it looks artificial, like a moon that's been painted. The leading explanation involves the dark hemisphere sweeping up dust and debris as it orbits, while the white hemisphere reflects sunlight too efficiently for the same darkening to take hold. A strange ridge running along its equator adds to the sense that Iapetus has had an unusual history. Beyond those four, Saturn's moon system contains multitudes. Rhea, Dione, and Tethys are mid-sized icy moons with heavily cratered surfaces and hints of past geological activity. Hyperion is small and chaotic, an irregularly shaped moon that tumbles unpredictably in its orbit, rotating in a way that's effectively impossible to predict far in advance. It looks in photographs like a cosmic sponge, and then there are the dozens of smaller, irregular moons orbiting far out from the planet, almost certainly captured objects, remnants of a more chaotic early solar system, still locked into Saturn's gravity billions of years later. 146 moons. Each one a world of its own, in some sense. Saturn's system, seen whole, is less like a planet with satellites and more like a small solar system in miniature. With Saturn at the center, the rings as its inner structure and an entire population of worlds spread out in every direction around it. Everything we've discussed so far rests on a foundation of data, and that data had to be collected somehow by spacecraft built by human hands, launched across billions of kilometers of empty space, operating far beyond any possibility of repair or rescue. The story of how we visited Saturn is, in its own way, as interesting as anything the planet itself has to offer. The first spacecraft to reach Saturn wasn't designed primarily to study it. Pioneer 11 was launched in 1973, initially targeted at Jupiter. After its Jupiter flyby, mission controllers used the planet's gravity to redirect it towards Saturn, a trajectory that hadn't been part of the original plan. It arrived in September 1979, becoming the first human-made object to visit Saturn, passing within about 21,000 kilometers of the cloud tops. What it sent back was limited by the standards of what came later. Pioneer 11's instruments were relatively simple, its cameras basic, but it confirmed that a spacecraft could navigate Saturn's environment without being destroyed by ring particles. It measured Saturn's magnetic field, and it sent back the first close-up images of the planet, blurry by later standards, but real. Proof that we could get there. The Voyager missions arrived next, and they changed everything. Voyager 1 flew past Saturn in November 1980, followed by Voyager 2 in August 1981. Together, they transformed Saturn from an astronomical object into a place. The images they returned were extraordinary. The ring system revealed in far greater complexity than anyone had seen before. New moons discovered, the hexagonal storm at the North Pole photographed for the first time, the atmosphere mapped in detail. Voyager 1's closest approach took it near Titan, and the decision to prioritize that flyby meant redirecting the spacecraft away from a trajectory that could have taken it onward to Uranus and Neptune. That trade-off was considered worth it. Titan, with its thick atmosphere and unknown surface, was seen as one of the most important targets in the outer solar system. The images Voyager returned of Titan showed only the haze. The surface remained hidden. Voyager 2, following a different trajectory, continued onward to Uranus and Neptune, becoming the only spacecraft to visit all 4 outer planets. But its Saturn flyby added significantly to what Voyager 1 had begun. More detail on the rings, more moons, more atmospheric data. Both spacecraft are still traveling. Voyager 1 is now the most distant human-made object ever built, well beyond the outer boundary of the solar system. Voyager 2 not far behind. They carry golden records containing sounds and images from Earth. A gesture toward whoever or whatever might eventually find them, long after everything that launched them is gone. Then came Cassini. The Cassini-Huygens mission was conceived in the 1980s, developed through the 1990s, and launched in October 1997. It was a joint project between NASA and the European Space Agency, one of the most ambitious planetary science missions ever attempted. The spacecraft took 7 years to reach Saturn, arriving in July 2004 after a complex series of gravity assists around Venus, Earth, and Jupiter. It carried with it a separate probe. Huygens, built by ESA, was designed to do one thing: descend through Titan's atmosphere and land on its surface. In January 2005, Huygens separated from Cassini and fell toward Titan. The descent took about 2.5 hours. Huygens transmitted data the entire way down. Atmospheric temperature, pressure, composition, wind speeds. Its cameras captured images of a landscape gradually resolving out of the haze below. Drainage channels. What appeared to be a shoreline. A flat plain littered with rounded pebbles of water ice, shaped by the flow of liquid just as riverstones are shaped on Earth. Huygens landed and continued transmitting for about 70 minutes before its battery died. It was, at the time, the most distant landing ever achieved in the history of space exploration. A probe, built on Earth, sitting on the surface of a moon orbiting Saturn more than 1 billion kilometers away. Cassini, meanwhile, settled into orbit and got to work. What followed was 13 years of continuous observation. Cassini made over 290 orbits of Saturn, conducted more than 160 targeted flybys of Saturn's moons, and returned hundreds of thousands of images. It discovered the geysers of Enceladus. It mapped Titan's surface through radar, revealing the lakes and seas that Huygens had hinted at. It studied the rings in extraordinary detail, resolving structures and dynamics that had been invisible from Earth. It found the ingredients for habitability in multiple places within a single planetary system. By 2017, Cassini was running low on fuel. A decision had been made years earlier about what to do when that moment came, not to let the spacecraft drift and potentially contaminate Titan or Enceladus with Earth microbes, however unlikely that risk might be. The solution was deliberate, planned, and in its own way, fitting. On September 15, 2017, Cassini was directed into Saturn's atmosphere. In its final hours, it transmitted data continuously: atmospheric composition, pressure readings, magnetic field measurements, right up until the signal stopped. It became part of Saturn. A spacecraft that had spent 13 years studying the planet was absorbed by it, returning the atoms it was made of to the system it had spent so long observing. There's something in that ending that's hard to fully articulate. The data Cassini returned is still being analysed. Papers are still being published from its observations. In a real sense, the mission hasn't ended. It just stopped generating new information. Everything it saw is still being understood, and there is still so much left to go back for. Saturn is the furthest planet visible to the naked eye. No telescope required, no special equipment, no particular knowledge. Just a clear night and the patience to look. For most of human history, that was enough to make it significant. A slow, steady wanderer in the sky. Different from the fixed stars, impossible to ignore once you knew what you were looking for. That visibility shaped everything that came after. Virtually every major civilization that kept records of the sky has a name for Saturn and a story attached to it. The Babylonians called it the Star of the Sun, associated with order, with justice, with the weight of time. The Greeks named it Kronos, the Titan who ruled before the Olympians, who swallowed his own children to prevent them from overtaking him. Rome renamed him Saturn and built an entire festival around him. Saturnalia, a midwinter celebration involving feasts, gift-giving, and a temporary suspension of social hierarchies. Some historians trace threads from Saturnalia through to modern winter holidays, though the connections are debated. What's consistent across cultures is the association with time. Saturn moves slowly across the sky, the slowest of the naked-eye planets, taking roughly 29 years to complete one orbit of the Sun. To ancient observers, that slowness felt deliberate, weighted, a planet that moved like something old and considered, not quick and impulsive like Mercury or bright and urgent like Venus. The personality they gave it matched the motion. Saturnine entered the language as a word for a particular kind of temperament: heavy, serious, slow to warm, marked by a kind of melancholy depth. It comes directly from the astrological character assigned to the planet, and it's still in use today. One of the few places where ancient astronomy has left a direct trace in everyday speech. Astrology built extensively on that foundation. In Western astrological tradition, Saturn is the planet of discipline, limitation, structure, and inevitability. It governs the things we cannot avoid. Responsibility, aging, consequence. A Saturn return, the moment when Saturn completes one full orbit and returns to the position it occupied at the time of your birth, is treated in astrological circles as a significant life threshold, typically occurring around age 29 and again at 58. Millions of people today still track it, still assign meaning to it, still feel something when they learn it's coming. Whether or not any of that reflects something real about the universe, it reflects something real about humans. That we look at slow, distant, inevitable things and find ourselves in them. Saturn has left its mark on art as well. Francisco Goya painted Saturn devouring his sun sometime between 1819 and 1823. One of his black paintings, a series of dark murals painted directly onto the walls of his house. It depicts the god mid-act, wild-eyed, consuming a human figure with a kind of desperate ferocity. It's one of the most disturbing images in the Western canon, and it draws directly on the mythological character of Saturn as something that devours what it creates. Time eating its own children. The image has become iconic in ways that extend well beyond its mythological source. The Voyager and Cassini photographs created their own kind of iconography. When Voyager returned the first high-resolution images of Saturn in 1980, they circulated widely. A ringed planet rendered in photographic detail for the first time, the rings casting clean shadows across the cloud tops, the moons visible nearby. Those images became part of how an entire generation understood what the solar system looked like. Saturn, more than any other planet, became the visual shorthand for space itself, the image most likely to appear on a poster, a book cover, a classroom wall. That association has never really faded. Ask someone to draw a planet, and the odds are reasonable they'll draw Saturn. Not Earth, not Jupiter. Saturn. The rings are too distinctive, too immediately recognizable. It became, somewhere along the way, the planet in the collective imagination. Science fiction has used Saturn and its moons extensively, though often as backdrop rather than subject. The rings appear as a navigational hazard, a scenic view, a staging ground. Titan has been imagined as a colony, a research station, a world being slowly terraformed. In Arthur C. Clarke's work, Saturn's system serves as a threshold, a place at the edge of the known, beyond which something waits. That feeling of Saturn as threshold, as boundary, as the last familiar thing before the truly unknown, maps onto something real. It is the last planet easily visible from Earth without assistance. Beyond it, Uranus and Neptune exist but can't be seen with the naked eye. Saturn marks the edge of the visible solar system as our ancestors experienced it. Everything beyond was darkness and inference. Standing at the edge of something vast and poorly understood, watching a slow light move through the stars. It's not hard to understand why they gave it the name they did. For everything Cassini showed us, it also showed us how much remains unanswered. That's not a failure. That's what good science does. It resolves one layer of questions and reveals the next layer waiting underneath. Saturn, after decades of observation and 13 years of continuous orbital study, is still a planet with open files, some of them surprisingly fundamental. Take the length of Saturn's day. That seems like it should be a simple measurement. Point an instrument at the planet, watch it rotate, time it. But Saturn has no solid surface to track, and its magnetic field, the usual reference point for measuring gas giant rotation, is almost perfectly aligned with its rotational axis, which makes it unusually difficult to use for timing. For decades, different measurement methods produced slightly different answers, and the uncertainty was uncomfortable for a planet we'd been studying so long. The resolution came from an unexpected direction. In 2019, researchers used oscillations within Saturn's rings, ripples in the ring structure caused by vibrations in Saturn's interior, essentially Saturn's own seismic activity, to calculate the planet's rotation rate. The rings, it turned out, were recording Saturn's internal behavior in ways that could be read like a clock. The answer they produced was 10 hours, 33 minutes, and 38 seconds. A basic fact about Saturn, settled by reading its rings. Saturn's interior remains only partially understood. The size and composition of its core is still uncertain. Whether it's a distinct rocky object or a more diffuse region where heavy elements are gradually concentrated, that distinction matters for understanding how Saturn formed and how it's evolved. Cassini's gravity measurements during its final orbits got closer to answering this than anything before, but the picture is still incomplete. The ring age question is similarly unresolved. The evidence points toward a relatively young ring system, but young is a range, not a number, and the mechanisms that would explain a ring-forming event 100 to 400 million years ago are still being worked out. What was the object that became the rings? How exactly did it come apart? Why did it happen when it did, billions of years into Saturn's history rather than early on? These are open questions with competing answers and no consensus yet. And then there are the moons. Enceladus remains one of the most scientifically urgent destinations in the solar system. Cassini told us there's a liquid water ocean beneath the ice, with hydrothermal activity on the seafloor, venting material directly into space. What it couldn't do was analyze that material in enough detail to answer the question everyone is really asking. A future mission, one designed specifically to fly through those plumes and carry instruments sensitive enough to detect complex organic molecules, amino acids, anything that would suggest biological processes, has been discussed seriously within the planetary science community for years. No such mission has been approved and launched yet, but the scientific case for it is strong, and it tends to get stronger as Cassini's data continues to be analysed. Titan has a mission on the way. NASA's Dragonfly is a rotorcraft lander, a drone, essentially, designed to fly through Titan's thick atmosphere and land at multiple locations across its surface. It was selected for development in 2019 and is currently targeted for launch in the mid-2020s, with arrival at Titan expected around 2034. The goal is to study Titan's chemistry directly, to look for complex organic molecules, to understand the methane cycle in detail, to visit sites where liquid water may have briefly existed on the surface following ancient impacts. Titan is thought to contain all the chemical building blocks associated with the emergence of life. Not life as we know it necessarily, not the water-based biology of Earth, but chemistry of a complexity that warrants direct investigation. Dragonfly will be the first mission to Titan since Huygens landed in 2005, almost 30 years between visits to one of the most remarkable worlds in the solar system. Saturn itself will eventually need another dedicated orbiter. The questions Cassini left open, the interior structure, the ring age, the full complexity of the moon system, are not going to be answered from Earth. They require proximity, time, and instruments built with those specific questions in mind. Proposals have been developed. The scientific community agrees on the value. The timeline, as with most deep space missions, remains uncertain. What isn't uncertain is that Saturn will keep doing what it does, regardless of whether we're watching closely. The rings will continue to slowly drain into the atmosphere. The hexagon will keep turning at the North Pole. Enceladus will keep venting its ocean into space. Titan's methane rain will keep falling on a landscape that has been cycling through its strange seasons for billions of years. The planet will keep radiating its internal heat outward, cooling imperceptibly slowly over timescales that make human history feel like a rounding error. There's something in all of that open uncertainty that feels fitting for a planet like Saturn. It has always rewarded patience. The astronomers who kept looking, even when what they saw made no sense. The mission planners who spent decades designing a spacecraft to go there. The scientists still working through data from a probe that burned up in 2017. The questions that remain aren't a gap in our understanding so much as an invitation. And some of the most interesting ones have less to do with what Saturn is made of and more to do with what it does, to the space around it, to the other worlds in its system, and to the broader architecture of the solar system it helped build. Saturn is not a passive presence in the solar system. It sits there, ringed and unhurried, and everything within its gravitational reach is shaped by it in some way. The moons, the rings, the smaller bodies nearby, all of it caught in a continuous negotiation with a planet that outmasses everything else in its neighborhood by an almost absurd margin. That influence starts close in and works its way outward. The rings themselves are a direct expression of Saturn's gravity. As discussed earlier, the Roche limit defines the zone within which tidal forces prevent material from coalescing into moons. But it's worth sitting with what that actually means in practice. Saturn is continuously pulling at the ring particles, stretching, kneading, preventing them from doing what gravity would otherwise encourage them to do, which is clump together and grow. The rings exist in a state of permanent tension between their own tendency to accumulate and Saturn's insistence on keeping them apart. Shepherd moons experience a version of this too. Small moons orbiting near the ring edges are in constant gravitational conversation with the ring material beside them. Prometheus, one of the shepherd moons of the F-ring, actually dips into the ring on each orbit and pulls streamers of material outward before releasing them again, leaving a repeating pattern of channels and knots in the ring structure that Cassini photographed in striking detail. A moon the size of a small city, reshaping a ring that stretches hundreds of thousands of kilometers simply by passing close to it repeatedly. Orbital resonances extend Saturn's reach much further out. The same mechanism that creates the Cassini division, the 2-to-1 resonance between mimas and the ring particles in that zone, operates throughout the moon system at larger scales. Moons lock each other into stable rhythms through repeated gravitational nudges. Some of Saturn's moons are in resonance with each other, completing orbits in ratios of small whole numbers. One moon completing 2 orbits for every one of another, or 3 for every 2. These resonances aren't coincidences. They're the result of long gravitational negotiations that have been running for billions of years, gradually nudging moons into configurations that are self-reinforcing and stable. Enceladus and Dione are in a 2-to-1 resonance with each other. That relationship matters more than it might seem. The gravitational flexing that results from Enceladus moving through that resonance is thought to be a significant source of the heat that keeps its subsurface ocean liquid. Enceladus is being continuously squeezed and stretched by the gravitational interaction, and that mechanical energy converts to heat deep inside the moon. The ocean that makes Enceladus so compelling as a potential habitat for life may exist, at least partly, because of the gravitational relationship between 2 moons in a specific orbital ratio. Gravity, at that scale, isn't just a force that holds things in place. It's a source of energy. Saturn's gravitational influence extends beyond its immediate moon system as well. In the broader solar system context, Saturn and Jupiter together act as a kind of gravitational architecture. Their combined mass dominates the outer solar system and their orbital relationship. The fact that Jupiter completes almost exactly 2 orbits for every one of Saturn's has shaped the distribution of smaller bodies throughout the solar system over billions of years. The asteroid belt, the Kuiper belt, the trajectories of comets falling inward toward the Sun. All of it bears the imprint of these two giants and the gravitational landscape they've created together. There's a hypothesis, still debated but taken seriously, that Saturn played a specific protective role in the early solar system. The idea is that Jupiter, left to its own gravitational influence, might have driven more cometary and asteroidal material into the inner solar system than actually arrived. Saturn's gravity, acting as a counterbalance to Jupiter's, may have dampened some of that bombardment, reducing the rate at which large impactors reached the rocky inner planets. Whether this made a meaningful difference to the conditions that allowed life to emerge on Earth is uncertain. But the question itself is worth holding. That Saturn, from more than 1 billion kilometers away, may have had some quiet influence on the world we live on. Saturn also generates something less visible but equally real. Its magnetic field, generated by the churning metallic hydrogen in its interior, creates a magnetosphere, a vast region of space around the planet dominated by Saturn's magnetic influence rather than the Sun's. That magnetosphere extends millions of kilometers in some directions, and it interacts constantly with the solar wind, with the ring particles, and with the moons embedded within it. Enceladus's geysers inject water vapor directly into that magnetosphere. Titan, which orbits near the outer edge of it, dips in and out depending on solar conditions. The charged particles trapped within the magnetosphere bombard ring particles and moon surfaces continuously, driving chemical reactions, darkening surfaces, contributing to the slow, ongoing transformation of everything in Saturn's vicinity. It is a system in motion, not chaotic, but deeply interconnected. Every component influencing every other, gravity and magnetism and orbital mechanics woven together into something that has been running, largely undisturbed, for 4.5 billion years. From a distance, it looks still. The rings appear frozen in place, the planet serene and unhurried. The moon's small points of light tracing quiet paths around it. But none of it is still. The rings are draining. The moons are nudging each other. Enceladus is venting its ocean. The magnetosphere is churning. Saturn is radiating heat from deep within, cooling by degrees over timescales we can barely conceive. Everything is moving, everything is connected. And at the center of all of it, holding it together, shaping it, driving it, a planet that floats. Until next time, keep your head up